The following is a basic AC design that leverages phase change for cooling. And on the left we have the hot side in red. On the right we have the cold side, which is in blue, which is liquid pipes. We have our refrigerant, which in this case is pollutants. The system itself is empty. So imagine getting a new AC system and it doesn't have any Freon, or they don't use Freon anymore, but it doesn't have any refrigerant in it. So we have our pressure regulator, which we use as a compressor, and it's set to 6,000. It compresses, it heats up. This becomes hot and liquids come out. This valve, condensation valve, allows only liquids to pass through. The gases stay. Liquids come out back here. They expand, which cools this pipe, this side. And then as it expands, we get more and more gas, and we heat this up. With a load on it, it creates more gas. So we pull that gas off with the purge valve. It is set at 3,000. And then we compress it back and around it goes. All right, but there's no refrigerant in the system, so we need a way to inject it. So what we have over here, we have a tank, and our tank is at 127, which would be about if you pulled it out of the Vulcan atmosphere using filtration device. You could also use the technique in the other video to extract pollutants, which gives you around 60, 70 Celsius pollutants. And this keeps this filled. It's set to 1,000, so it's just designed to add gas. So we'll start this up and we'll start injecting gas here. We'll start a compressor and we'll start our purge. Now you notice here that the hot side is still at 127. It hasn't increased. Now this is not how real physics work. In this case, it only heats up during a transition of gas to liquids, where the heat is moved from the liquid to the gas. And so in our case, wrong one. All right, so we need our temperature is 126 or 127, around that. And so we need about 53 or so, 100 kPa before we'll start generating any liquids. Now this circuit is very simple. You would have on this side something to pull this waste heat off, and this would charge, cool down whatever you want. In later part in this video, we'll chain two of these together. And here we are getting close. Now, as I comment later on in the video, the pressure regulator was used for convenience. This whole design you see here is designed to be very simple, to try to explain the most basic layout of a phase change AC system. Once the principles are sort of nailed down, then the next step is to make changes to the system to improve performance. All right. So the pressure is high enough, as you see. Now we generate liquids, and the temperature is going up. And as the temperature goes up, the pressure required goes up. The temperature will go up to high enough that will no longer generate liquids. So we notice if the temperature gets too high, around that 150th mark, we can't have any more liquids. So we'll shut down at that point. And we're just about to hit that point. And then liquids will stop. And this side is down to 64. And here we have, 127, because that's what the gas we're injecting, and it's at 1 megapascals as we set. So I don't think we've actually, this will move, this is set to 3,000. So if the pressure exceeds 3,000, it will then move gas over. And this valve now is designed to control the temperature, but there's a maximum delta between the hot and cold side. So if you look at the chart and go, well, we'll put it on, let's see, we put it at 3,000. That means it should be, around -16. Well, that doesn't happen because from experiments, it seems you can get about 50 to 60 to 50 degrees Celsius delta. And as you push that, it slows down the process. So, say a safe 50 degrees Celsius between stages. So if you want to lower down, say 100 Celsius, you'll need 2 stages. One stage will not do it no matter what you set this at. Now look at this design. This is actually what 2 chambers, I believe, would look like internally. So one chamber, and you notice we have the 2 dials. So on the condensation chamber, you have a pressure gauge that you set. And you have a hot side, and you can bring waste gas out. And you have liquids that come out. So about this part, right, these 2 right here would be part of that of the condensation chamber. And then you have the evaporator, which takes liquids in, spits gas out, and also has a setting here, internal purge valve. Injection is something you're still responsible for. It's not handled by the chamber, so you still have to have a way to inject gas. In that gas line between the 2 chambers, you'll need to add gas to that. But this is also way more compact than using those chambers. And I always find it difficult to run the piping between 2 of them. I can't find a good configuration. They use a lot of space. This is a far more compact design. Now, how does this perform against a chamber? I don't know. And, one weakness is using the pressure regulator versus, say, using a turbo pump with an analyzer. So, and that would require an IC to control this. Is the volume used here too small? As you see in previous video, increasing volume of the hot side increases the amount of liquids that pass through. So possibly making this larger, maybe using additional condensation valves. Do we have enough? Now, right now, since the pressure here is below 3,000, it's keeping up right now. But maybe if we add more capacity on this side, we have to add a little more capacity on this side. Can we inject pollutants a little faster? Are we keeping up? We seem to be keeping up. Probably because right now we're shut down. So right now it's too hot, so it's not generating any fluids. So when you look at this design, my belief this what matches what 2 chambers would be internally. I also believe this is the minimum layout, or this is the only layout you require. Now you can change components to make it faster and more efficient, like change the pressure regulator to a volume pump with a pipe analyzer and an IC chip, but that doesn't change the functionality. It compresses gas. So you have a high pressure side, you have liquid side, and you have a low pressure side. You have your dial you use on your one chamber, another dial you use on another chamber. You have 2 dials. And this component here that injects pollutants, the chambers do not support that directly. You still have to do that manually on your own. So so the next we'll do is redesign this and put 2 together, and we'll see how well that works. Now, in this experiment, we could add a radiator to this, put in and then radiate outside, because outside on Vulcan is 126. And we lower this temperature down, then it will continue to operate. But we just want to show the basics of AC systems. This should all make sense, right? This is the base crust part of it. And I can't think of a way to make it any simpler, right? This is trying to, so if you have suggestions on that, please let me know. Okay, so we're going to try this again, but with 2 stages here. So here we go, our first stage. You notice we do not have the hot side connected to outside yet, or in a sink. The other change is that we have a one-way valve for the refrigerant. And this is so we only need one pressure regulator for multiple stages, or all the stages. And the regulator is down here, so we pressurize the line, and then each stage uses just a simple one-way valve. So this is identical to what we had before. We have the second stage, which is identical to the first stage, and they're connected using a simple heat exchanger. Now, as I stated before, the goal of this is for demonstration, not necessarily the most efficient way of building this. So I'll keep it as simple as possible. And another factor too is by building this out, you can create a baseline and then create other configurations and compare it against this configuration to see, does it actually improve or not improve. For example, if I put a storage tank right here or add a storage tank to the hot end or the cold end, does that improve efficiency in operation or not? But for this initial one, I just want to keep it as simple and remove all the extra complexities. All right, let's turn on our compressor, our purge. So we have 6,000 here. Yeah, 3,000 here. And on the second stage, turn compressor. We have 6,000 here. Our purge, and we have 3560. The reason for 3560 is that based on our chart for pollutants, that should give us, in theory, 20 degrees Celsius on this pipe. All right, so the first thing we need to do is charge up the system because we're first starting. And another concept is having an auto start system. So you build it all out and then you just kind of start it and it'll auto prep itself and not have to have, independent tasks to, charge a bunch of lines and disconnect them and play those kind of games. Now, I pre-collected this pollutants, but from the previous video, you could auto-generate it from the atmosphere during night. All right, so we're still going here and going here. And until we have liquids, we won't have a temperature change. And there we go. So now, and the heat is building up on this side. And as before, initially this pipe's a little chilly, probably because we have a heat, all the heat's been sucked out over here. Okay. So we're not target yet. Not sure why this is running. Oh, I turned the other one on before. And we have nothing over here. All right. All right. So after multiple night-day cycles, we finally have our last stage down to 24.6. And the hot end is 93. And we got 91. And we started a day cycle, so we're heating back up again. All right. So this obviously, quote unquote, works. It's not definitely not the most efficient design, but it's functional. And, for example, here I'm letting in, heating this pipe back up during the day. And other solutions for this, for example, if I had a big insulated tank outside and filled it at night and give it a lot of mass so it could probably run partly through the day and then dump it and then refill it on the next night cycle would help there. Probably using a volume pump, turbo pump here would help. Unknown if we should replicate either one of these. There's adding some additional volume on the hot end and the cold end, maybe even on the low pressure side of things. And really working hard to get down, in theory, because at the pressure set, it should go down to 20, but it's having a hard time. So maybe it really requires 3 stages to improve the efficiency, to get it all the way down to just 2 stages is a little bit too much to ask for. And you'll definitely need a multi-stage approach. And then at some point, you would have to change refrigerant if you keep going down further and further cold. And so right here we have pollutants, but at some point we may have to switch some other refrigerant if we want to take it very low. All right, so that's the end of this set of experiments. I think the next video we'll look at improving the efficiency of this, making we'll set up a control and probably just do 1 stage at a time. We'll take 1 stage and we'll replicate the 1 stage and then make changes to it and see which one can get the the cold side, the coldest, the fastest, and work from there and just kind of play around with the designs. But yeah, it's obviously you can cool using just phase change. It's not super straightforward. Well, actually it is straightforward, but making it efficient, it's going to be a little more difficult. Maybe if I just threw 3 stages at it and just give it some cook time and just not worry about it so much, would do better. My guessing is pressure regulators is just not the right solution. And obviously we would need, instead of storing the pollutants, we would just extract it at night and do something there. But that's something you can place this side without impacting the other parts. So that's this set of videos. I'm trying to, so the goal of this video was to try to make it very simple and straightforward, the layout of how this works. All right, until next video, see ya.